All right, this is the last lecture in the ordinary differential equations unit of this course. So today we're going to talk about, we've talked about accuracy, but now we're going to talk about numerical stability. So the goal is to study the asymptotic behavior of numerical ODE solvers. So let me remind you first about what we've sort of established, sort of the asymptotic behaviors of these ODE solvers so far. Previously, we talked about the convergence of Euler's method, so that the asymptotic nature of the accuracy with respect to step size went like this. If we let h go to 0, then the number of steps goes to infinity, and then we expect the Euler's method, or the numerical method, to converge to the true solution with some convergence, order h in terms of Euler, h squared for modified Euler. So that's the type of convergence and asymptotic analysis of the accuracy. Now that's as the step size goes to 0. So the step size goes to 0, these numerical methods converge to the true solution. Now let's talk about a different kind of asymptotic thing. Now it's not the step size going to 0. Now it's the time going to infinity. Okay, so we're going to study the numerical stability of these methods. This is h fixed. The step size is fixed, but now the number of steps is going to go to infinity. Before the number of steps went to infinity as the step size got shorter. Now the step size is fixed and we're going to go to infinity. So this is really relevant, really only relevant if we're expecting our solution to settle down to some equilibrium, which is the way a lot of systems do work. Some of them converge off to infinity somewhere, like let's say exponential growth of a population. It starts off slow, but I mean it grows and grows and grows and grows, unbounded in theory at least. So in those cases, who knows? The numbers just get big and they just take off, and we're not talking about that. We're talking about the case where there's like a negative growth or population decline, and we expect the population to sort of go down, 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 and we expect it to go converge asymptotically to 0. Of course, in real life, you can't have less than one individual, so it would eventually click to 0. But anyway, you get the idea. There's a theoretical model converging to an asymptotic solution, converging to an equilibrium solution. There are other equilibrium solutions, by the way. Let's say you've got a population of rabbits that keeps reproducing, but then every day the hunters go out and catch a certain number of rabbits. So you could get this equilibrium state where the number of rabbits sort of the hunters go out and they try to hunt rabbits. The more rabbits there are, the more they'll catch. So as the number of rabbits increases, the hunting is more successful, so the number of rabbits decreases, and this sort of dynamic thing you typically reach an equilibrium. A non-zero number of rabbits equilibrium, maybe 150,000 rabbits in the region is the equilibrium, where the number that are harvested by hunters each day equals the number that are born on average each day. Okay, so it's this equilibrium, it's this asymptotic convergence to an equilibrium solution that we're interested in. And we want to make sure that our numerical algorithms, our numerical solvers, duplicate that convergence process. Okay, so so where am I now? We want to study how close y sub n, our estimated solutions, remains to y of x for large x. So as x gets big, we want our solution to be close to the true solution. This does not depend on the initial value problem itself. I mean, the analysis we're going to do is not specific to the initial value problem. In fact, once you get close to an equilibrium, all differential equations kind of look the same. They all kind of look like they're just converging, and it's like when you have a circle. If you zoom in on the edge of the circle, you keep zooming in, it always just looks like a line. If you zoom in on the edge of a circle. Similarly, when you zoom in close to an equilibrium, they all kind of show the same sort of asymptotic behaviors. So we study the test equation. Now the test equation is basically just a generic equilibrium or generic convergence to an equilibrium. So, right, I'm switching this. So the test equation is y primed equals negative lambda times y, where lambda is a positive number. So this is basically exponential decay at rate lambda. And we're going to start at y of 0 equals 1, but it's irrelevant, really. Doesn't really matter. So the solution of that's a linear differential equation. We know the solution. It's y of x equals e to the negative lambda t. So that's exponential decay. And as x goes to infinity, y of x goes to 0. And this is since negative lambda is less than 0. Negative decay rate, or a decay. So for numerical stability, we require that the limit as n goes to infinity, number of steps goes to infinity, of y sub n also equals 0 for this test equation. And this test equation, like I was saying, once you zoom in on an equilibrium, they all look the same. So wherever your equilibrium is, you just like move it to 0, and then you expect your solutions to converge to 0. So let's look at the stability of Euler's method. So here's Euler's method, y sub n plus 1 equals y sub n plus this linear step. Now what we're going to do is plug in, instead of using f, we're going to plug in the actual right-hand side of the differential equation, right? It's y sub n plus h, and that f thing comes from this thing up here, negative lambda times y. Okay, and we can rewrite this as 1 minus lambda h times y n. Okay, so now that's for one time step, but notice this multiplier in here is the same for every time step. So we can actually simulate many time steps. We know that y sub n plus 1 is 1 minus lambda h to the nth power times the initial solution. So in order for that solution, for that numerical solution, that sort of iterated Euler's method solution to go to 0, we need the thing inside that exponential, 1 minus h lambda, to be smaller in size than 1. Okay, because if it is, raising it to a higher power makes it smaller and smaller and smaller, and that therefore h sub n will go to 0. So let's look at that. That means that negative 1 is less than 1 minus lambda h, which is less than 1. Or let's move this 1 out of here to both sides. So we get subtracting 1 from everything. Minus 2 is less than negative lambda h, which is less than 0. Okay, or we can say 0 is less than lambda h, which is less than 2. I just multiplied everything by negative 1. Okay, first of all, this inequality, 0 is less than lambda h, is easy because lambda and h are both positive. Okay, so that's no problem. The more interesting one is the second one. So you got lambda h less than 2. That's not necessarily obvious. In fact, it really just leads us to h must be less than 2 over lambda. And we typically write it h less than 2 over the absolute value of lambda. Why is that? Well, lambda is positive, so let's not do that. When I used to teach this course, we used to use lambda being a negative number, so that's why the absolute value sign was there. But since lambda now, I think it makes more sense. It's easier to interpret this analysis when lambda is a positive number, so we don't have to take the absolute value. Okay, so the message here is that a large lambda means we have to take a small h. This inequality has to hold in order for this inequality to hold, which is what we need to be true in order for it to converge. If that inequality doesn't hold, then this inequality doesn't hold, and vice versa. Anyway, so in order to guarantee the convergence of Euler's method, we need to make sure h is less than 2 over lambda. So a large lambda means we have to take smaller time steps. Faster decay means we have to take smaller time steps to be stable. So this dependence of h on lambda is called conditional stability. Because the stability is conditioned on our time step relative to our convergence rate. Okay, so let's look at a different method. That was Euler's method. Okay, let's look at a different method. In fact, let's look at a different family of methods. The methods we've looked at so far are called explicit methods because we have an explicit formula to calculate the next point based on the previous points. So next point equals something that involves previous stuff that's already been calculated. An implicit method yields an equation involving the next point as well as the previous point, but it must be solved to find out what the next point is. So it's not next point equals some formula. It's some equation that involves the previous point and the next point, and we have to solve for y sub n plus 1 in order to figure out what the next state should be. So I'll show you an example of that. It's called the trapezoid method. So here's a differential equation, y prime of x equals f of xy. If we were to imagine integrating both sides, we could get this equation. We're going to integrate it over like one time step, if you like. So let's call this over here left-hand side, and this over here is the right-hand side. So let's look at the left-hand side first. If we knew what, let's pretend for now that we know what the solution, what the antiderivative of y primed is. It's y of x. So if we know the antiderivative, we can actually write out, like use the fundamental theorem of calculus to write out the integral like that. And so we get this thing over here. It's basically the fundamental theorem of calculus. It's y evaluated at the endpoint minus y evaluated at the beginning. Okay, that's the left-hand side. Now let's look at the right-hand side. So how do we, you can see a joke's coming. Why don't I just say the joke now? Joke break. So what if I don't know what Armageddon means? It's not the end of the world. Okay, the right-hand side is this integral of the dynamics function f. Now we don't know what f is, so best we can do is just kind of come up with some strategy for computing it. We'll use the trapezoid rule. I'm describing the trapezoid method as an ODE solver, and the trapezoid method is based on the trapezoid rule for computing integrals. So the trapezoid rule goes like this. I'm always afraid to put my hand down on my iPad. Trapezoid rule. So when computing the integral xn to xn plus 1 of f of x, y of x, dx, we look at this drawing over here on the right. And what we do is we draw a straight line between these 2 points. Now this shape inside here is a trapezoid. And we're going to compute the area of that trapezoid. That's really easy. It's basically, so it's like computing the area of a rectangle, except you just take the average of these 2 heights. And that gives you the area of that trapezoid. So I can write the area as, well, the area is approximately 1/2 the function value at one side yep, bigger bracket here, plus the function value at the other side. times the width, h. So the average of the two heights times the width. So that gives us, now if I call this equation up here 1, that's like my integral equation, but we can turn it into a differential equation. So 1 turns into this thing here. The left-hand side, remember, was over here. So I'm going to call that y sub n plus 1 minus y sub n equals this thing up here, 1/2. Actually, I'll just call it h over 2 f xn yn plus f x n plus 1 yn plus 1. So the thing to notice here is it's an implicit method because yes, we have yn plus sub n plus 1 over here, but we also have it over here kind of wrapped up inside this f. So it's not as simple as just evaluating the formula and now we magically know what yn plus 1 is. We'd have to, I mean, it would really depend on what that f is. We'd have to solve that equation for y sub n plus 1 to figure out what the next time step is. That's an implicit method, implicit. The global error for the trapezoid method is h squared. So that matches the modified Euler method, but it does have different properties. Because it's an implicit method, it does have different properties, and you'll see that in a second. So to find y sub n plus 1, you have to solve a possibly nonlinear equation. It depends on what f is. If f is really easy, if it's just a bunch of like linear terms, then it's easy. If f involves cosines and logarithms and higher order exponents and things like that, it can be really hard. In fact, maybe then all you can hope for is a numerical solution. So you have to like numerically find the root of that equation before you can take the next step in your numerical ODE solver. Implicit methods tend to be more numerically stable than explicit methods. So stable meaning what I'm talking about in this lecture. Stability being the properties of going towards, of converging to an equilibrium when the real system does. So these implicit methods tend to be better at converging to equilibrium than the explicit methods. It's useful for stiff systems. So stiff system is a system where you have it's a system of differential equations. Some variables are changing really quickly and some are changing really slowly. So you'd like to take big time steps because of the things that are changing slowly, but you can't take big time steps because some things are changing really quickly. So that forces you to take shorter time steps. These implicit methods tend to be better at balancing those two different scales of time. Let's look at the stability of the trapezoid rule, the trapezoid method, sorry. Again, we're going to look at, I'm sorry, I know I changed the notes here, but it's just easier to understand. In fact, this change of making lambda positive now instead of negative, making it positive matches the course notes. I just forgot to update your notes before I distributed them. Okay, so there's the test equation. The same test equation. Whenever we're studying stability, it's the same test equation. Okay, so here's our sort of, this is our trapezoid method here, right? When we were studying Euler's method, we had a different formula there. When we were studying the stability of Euler's method, we had a different sort of schema for computing the next point. This is the trapezoid method, so we use this schema. Okay, but since we're using the simple test equation, we know what these f's are. We know what these f's are. So we can just plug in the formula for f. So y sub n plus h over 2. This is negative lambda yn minus lambda yn plus 1. Now we solve this for y sub n plus 1. So this is an example of a version of the f that makes it easy to solve for yn plus 1. It's implicit, but it's easy to solve. So y sub n plus 1 on this side, we'll have 1 plus lambda h over 2 equals y sub n 1 minus lambda h over 2. Okay, so then solving for yn plus 1, it's 1 minus lambda h over 2 over 1 plus lambda h over 2 times yn. Okay, so that's sort of equivalent to way up here, this formula that we had for Euler's method. Okay, so we could do the same thing where we say y sub n plus 1 is that whole thing inside there to the nth power times y0. So again, what we need is the thing inside those big brackets to be smaller in size than 1. Notice that, though, it's always smaller than 1 in size. For any h. Because lambda h is positive, this numerator will always be smaller in size than the denominator. Yes. Even if it's negative, it'll still be smaller in size. So this means it's unconditionally stable. I kind of wish I left a little more space there. There. This is called unconditional stability. It's unconditionally stable because the step size has no impact on whether or not it converges. It converges for any step size. So this is nice because we can take larger step size and still expect it to converge. So these stability properties or characteristics or behaviors are a function of the ODE numerical solution technique, not the differential equations you're dealing with. Those differential equations do matter, but for different things. In terms of converging to the equilibrium, this stability analysis is a property of the numerical method we're using to solve. Runge-Kutta 3, modified Euler's, trapezoid rule, each of those has its own stability characterization. So modified Euler has the same stability as its conditional stability, same as Euler's method. H has to be less than 2 over lambda. And just for some reference, Runge-Kutta is also conditionally stable, but H has to be less than 2,785 over lambda. So it's conditionally stable also, but it's got a much larger h. It's like 1 over 1,000 times bigger time steps that you can take and still have it converge properly to an equilibrium. So that's stability for these numerical ODE solvers. And that's the end of the ODE unit. I hope you're enjoying working on the assignment. It was a lot of fun for me making it. And next, we'll move on to the next unit, which I think might be interpolation. I'll see you then.